These are some helpful hints for the homework entitled Chapter 6, Part 2. Try these before you listen to the hints on them, just to give yourself a shot. First one is about an arcade game in which a disc of a given mass is shot across a horizontal frictionless surface, maybe like an air hockey table, by compressing it against a spring and releasing it. We're given the spring constant of the spring and the distance it's compressed from its equilibrium position, 5 centimeters or 0.05 meters. Find the speed with which the disc slides across the surface. So in this case, we can use the known spring potential energy formula, 1/2 kx squared, to help us solve this problem. So to do that, we'll take the system to be the disc plus whatever the spring is attached to, essentially the earth through the other end. And we'll take the spring force, importantly, to be an internal force, and so it has an associated potential energy term, 1/2 kx squared, where x is how far the spring is compressed from the equilibrium position. So in this case, we would have the net work done by all, so I'm going to take initial to be the compressed configuration and final to be when the puck just leaves contact with the spring, and we want to find out what its speed is in the final case. So we'll use that relationship, the net work done by all external forces equals delta Ke plus delta Pe, and in this case, since we're taking the spring force to be an internal force, there aren't any other external forces that do work. The normal force is acting on the disk as it moves, but it's not doing any work because it's perpendicular to the direction the disk is moving. Same thing with the weight force, so that neither of those are doing any work on the disk as it's accelerating and the spring decompresses. So the net work done by all external forces is 0 because they all do 0 work, and that's equal to delta Ke plus delta Pe, 1/2 mv final squared minus 1/2 mv initial squared, where v initial is 0. Plus 1/2 kx final squared minus 1/2 kx initial squared. The x initial is 0.05 meters, and x final is 0. That's when the spring is completely uncompressed and it's in its relaxed equilibrium position, which is always, by definition, x equals 0. So if you put all that down, you'll find that the only unknown is v final, which represents the speed after it has been released by the spring. 2 concerns a bead on a loop, and it's sliding on this wire without frictionless, on a frictionless wire, so there's no friction as it slides. The bead is released from a height of 28.2 meters above the bottom, and there's a loop that has a radius of 9 meters or a total height of 18 meters. What's the speed at point A? So that's at the top of the loop here. And we're going to take our system, in this case, to be the bead plus the earth, and gravity between the bead and the earth we'll take to be an internal force. So we'll associate a potential energy with that conservative internal force. And just because I don't really know what else to do with it, I'm going to take the normal force from the wire that's pushing. It doesn't have any component of force from the wire parallel to it because it's frictionless, but it does have a normal force that it exerts on the bead. It's going to do 0 work because the normal force is always pushing perpendicular to the direction the bead is moving. And we'll use our relationship, the net work done by external forces is equal to delta Ke plus delta Pe. The delta Pe is the gravitational force, but there's no external forces that are doing work. The only external force we left in there is the normal force from the wire, and it does 0 work because it's always pushing perpendicular to the direction the bead is sliding. If it weren't, it would be acting like friction. So the left-hand side is 0, and the right-hand side is delta Ke plus delta Pe. That's 1/2 mv final squared, where final is position A, minus 1/2 mv initial squared, where initial is the starting position pictured, plus delta Pe, and delta Pe is mg y final minus y initial. So in this case, mg times y final minus y initial will have y final minus y initial is a negative number because it's going down from the initial to the final, so it will be minus this distance here, which is 28.2 in my version, minus 18 meters, which is the height of this above the ground. 28.2 minus 18 is 10.2. So this distance is 10.2. It goes down by 10.2. So we would have for delta PE minus m times g times 8.2, a negative change in potential energy. And then we would have V initial is 0, and we want to know V final, which is at A. So 1/2 mv final squared minus 1/2 mv initial squared plus that negative change in potential energy term. Solve for V final. That's the speed at point A. And problem 3, an ore car of mass 42,000 kilograms starts from rest and rolls down on tracks in a mine. At the end of the tracks, it's 6.8 meters lower, closer to the center of the earth, in other words. And at that point, there's a horizontally situated spring with a spring constant there. How much is the spring compressed in stopping the ore car? So it's starting from the rest, so we're going to take our initial to be when it's initially released from rest, and the final to be when the spring is maximally compressed and the cart has momentarily come to rest there before being pushed backwards. So it starts at rest and it ends at rest, and that means the change in kinetic energy is equal to 0 because the kinetic energy initial and final is both 0. So in this case, if I take my system to be the cart plus the earth, and we're going to take both the gravitational force and the spring force to be internal forces, so they'll have a potential energy associated with them. There are no other forces that are doing work on the moving part of the system, which is the cart. The only other force that's doing work on it besides gravity and the spring force, or that might be doing work, is the normal force upward on the wheels. And in that case, it's always perpendicular to the direction the cart is going, which means it does 0 work. And so we'll use the same relationship I've been using. The net work done by external forces is equal to delta KE plus delta PE, and in this case the net work done by external forces is 0 because the only forces doing work are gravity and the spring force. They're internal. So 0 equals delta KE, we already decided that was 0, plus delta PE. Delta PE is equal to m times g times minus 6.8 meters, since it's gone down vertically 6.8 meters. That's the potential energy change due to the gravitational force. Then we also have a potential energy change due to the spring force, which is 1/2 k x final squared minus 1/2 k x initial squared. Initially, the spring wasn't compressed, so we would say x initial is 0. The spring didn't have any potential energy in it. But finally it did, so we would have a 1/2 k times x final squared. And it's that x final squared that represents, that x final is how far the spring is compressed in that final position. So our goal there is to solve for x final. And I think we have all the other pieces needed. Problem 4, there's a girl on a swing. We know some heights here, and we want to know what is her speed. Oh, by the way, I should say on this problem here, we're not given the mass of the bead, but that's okay. The mass cancels out. When you put everything down, you have a common factor of m on one side and a 0 on the other side. Same thing's true up here in this problem with the girl on the swing. We're not given her mass. The mass will appear in the equation I'm going to say out loud, but it will cancel out. So we're going to take the system to be the girl plus the earth, and gravity is the only internal force. The normal force that's coming from the tension in the rope is actually going to do 0 work because it's always pulling in a direction perpendicular to the direction the girl is going at that instant. So the rope force does 0 work. It's an external force, but it does 0 work. So in this case, the net work done by all external forces, only external force is the rope force, that does 0 work in going from the initial up here to the final, which is the very lowest position. And that's equal to delta KE plus delta PE, 1/2 mv final squared minus 1/2 mv initial squared, and v initial is 0. because initial is the very highest point where she's not moving. And V final is what we want to find. Plus delta PE, and that's mg y final minus y initial. And y final minus y initial is going to be a negative number, negative times 3.3 minus 0.7, whatever that is. Put the minus sign in front of it, and that's delta y. So in that equation, 0 equals delta KE plus delta PE, you'll find that V final, where final is down here, is the only unknown. That's what they're asking for. Problem 5. There's a block on a vertical spring, so a spring that's aimed upward toward the sky. We're given the spring constant. It's compressed down by a given distance from its equilibrium position. And when it's released, the ball leaves the spring and travels upward vertically. How high does it rise above the point of release? So in this case, I'm going to take, again, just because it makes life easier, I'm going to take the spring force and the gravitational force to be internal forces. My system is going to be the block plus the earth, and the spring force and the gravitational force will be between those two pieces. And there are no other external forces acting on the moving parts of the system. So when we do the net work done by external forces is equal to delta KE plus delta PE, the left-hand side is 0. I'm ignoring air resistance. It seems like that's what we're supposed to do here. And so 0 equals 1/2 mv final squared minus 1/2 mv initial squared. Well, v initial, I'm going to take initial to be when the spring is really when it's released from rest. The mass isn't moving then, so there's no initial kinetic energy. V initial is 0. And final is going to be when it's at its very highest position. It's also not moving there, so delta KE is actually 0 here because it starts and ends with 0 kinetic energy for my definition of initial and final. Plus, so we need, that's delta KE plus delta PE. And there are two terms for delta PE. There's a change in gravitational potential energy plus the change in the spring potential energy. And in this case, the change in gravitational potential energy is mg times y final minus y initial. And that y final minus y initial is what we want to solve for. So think of that thing in parentheses as our variable. Plus the change in spring potential energy. Initially, the spring has potential energy 1/2 times this k times this x squared, and finally it has 0 potential energy stored in the spring because when the mass is way up at its highest point, it's not touching the spring anymore. The spring is totally decompressed, so it has 0 potential energy. So 1/2, so we would have 1/2 k x final squared minus 1/2 k x initial squared, and x final is just going to be 0 because the spring isn't compressed at all there. When you look at that, I think the only unknown in that equation will be the y final minus y initial. So you can solve for that. 6. The radius of Mars is given, and the mass is given. An object is launched straight up from just above the atmosphere. That's essentially at the surface of Mars. The atmosphere isn't very thick. What initial speed is needed so when the object is far from Mars is code word for saying essentially our final is infinity. We're going to set the final radius of the object relative to the center of Mars to be infinity. When r is infinity, its final speed is 1,000 meters per second. So in this case, we're going to take our system to be the object plus Mars, with gravity being an internal force. There aren't any external forces. So the net work done by external forces is 0. That's equal to delta KE plus delta PE, 1/2 mv final squared minus 1/2 mv initial squared. V initial is what we're looking for. V final is the 1,000. Okay. And then we need plus delta PE, and delta PE is going to involve that formula minus G m1 m2 over r. Okay. We got to be very careful, as I showed in the videos, to keep track of those minus signs. So we have minus G m1 m2 over r final, and r final is infinity, so that's going to go to 0, minus, in parentheses, minus G m1 m2 over r initial. R initial will be the radius of Mars because it's essentially at the surface. When you put all that in, you'll find out that the mass of the object cancels out. We're given the mass of Mars, and the only thing that we won't know in that equation will be the initial speed, v initial, so we can solve for that. They change it up in part 2, problem 7, which asks, forget about that, we want to do a lower initial speed so that it keeps going, it never falls back to Mars. It keeps going, but it eventually gets closer and closer and closer to being at rest, even though it never comes back. So it gets infinitely far away, but approaches a state with a final speed of 0. So in that case, same equation as before, and the only difference is going to be that we set v final equal to 0 rather than the v final equals 1000 as we did up there, and solve for v initial again. Problem 8, an object is released from rest a certain height above Earth's surface. Since I think r here is supposed to be the radius of Earth, I take it. That really should say the radius of the Earth. So 1.02514 Earth radii above Earth's surface. So that means we have to add on the radius of the Earth to get the initial r to put in our potential energy term. Okay, and blah, 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 blah. Find the speed of the object when it strikes Earth's surface. Neglect atmospheric friction. That means air resistance. Of course, that's completely ridiculous. Atmospheric air resistance would have a huge effect on the final speed of this, but we're supposed to imagine that the Earth doesn't have any atmosphere in this problem. So in this case, I would take the system to be the object plus Earth, and the gravitational force is internal. Since we're neglecting air resistance, there aren't any other forces doing work on the moving parts of the system. And therefore, the net work done by external forces is 0. That's equal to delta KE plus delta PE. So that's 1/2 mv final squared minus 1/2 mv initial squared plus minus gm1m2 over r final minus, in parentheses, minus gm1m2 over r initial. Excuse me. And in this case, r final is going to be the radius of the Earth, and r initial is going to be the radius of the Earth plus this amount, where I think that's supposed to be the radius of the Earth there, if I understand correctly. In that case, we can find out, since v initial is 0, the only unknown in that equation will be v final, the speed right before it strikes the Earth's surface, so we can solve for that. Planet 0 has a mass of so many kilograms and in such a radius. A space probe is launched vertically from the surface with an initial speed of 5 kilometers per second. I would immediately change that to meters per second, just to be safe. Put it in SI units. What's the speed of the probe when it's so many meters from 0's center? So that means this is our final, and our initial is going to be the one at the radius. So I'm going to take the launch to be initial, and the final is when it's at this radius from the center of 0. And we can, same thing we're doing in all of these homework problems. The net work done by external forces, I'm going to take my system to be the object plus 0. Gravity is an internal force. No other forces are doing work. I think we're supposed to assume that there's no atmosphere on planet 0, even though it doesn't say that. And so we have 0 equals 1/2 mv final squared minus 1/2 mv initial squared. Our v initial is 5 kilometers per second, changed to meters per second. And v final is the answer to the problem. And then we're going to have plus the change in gravitational potential energy plus minus g m1m2 over r final, where r final is this distance, minus, in parentheses, minus g m1 m2 over r initial, and r initial is going to be the radius of planet 0. And I believe when you simplify all that down, the only unknown will be the final speed, v final, which is the answer to the problem. Hemispherical bowl. So a particle is released from position A at rest, and we're given the radius of the bowl, the mass of the particle. I would change to kilograms. The radius is in centimeters. I'd change to meters. Calculate the gravitational potential energy at point A relative to point B. That means gravitational potential energy at A minus the gravitational potential energy at B. And that's going to be equal to the mass of the object, mg, times y at A minus y at B. Y at A minus y at B is just r. So it's just going to be m times g times r. And it's positive because it has more potential energy here than there. Calculate its kinetic energy at point B. So in this case, I could take my system to be the block plus the Earth, and the gravitational force could be internal. So I'll associate a potential energy with that. And I'll take the normal force to be external. Doesn't really matter because the normal force isn't doing any work on the sliding block at all because there's no friction here. And so the bowl force is just the normal force, and it's always perpendicular to the direction the block is moving. Therefore, the net work done by all external forces is just the work done by the normal force, which is 0, and that's equal to 1/2 mv final squared minus 1/2 mv initial squared. V initial is 0, V final is the answer to our problem, plus the change in potential energy, which is going to be the negative of the answer we gave in the previous problem. So it's going to be minus mg times r, because it goes down in potential energy and going from A to B. Solve for V final. And that would be the answer to part 2. Part 3, calculate its kinetic energy at point C, which is a height 2r over 3 above the bottom. So again, I could take initial, my same system. This is initial at A, final is at C. It looks like it's a distance 1r over 3 closer to the Earth than it was at A. And so the change in potential energy is going to be minus mg times r over 3. And so same kind of thing. Instead of it, the only difference between this one and the previous one is instead of a bigger change in potential energy, it's going to have a smaller change in potential energy. But you could find, oh, in this case, I guess we're not asked for the speed here, but rather the kinetic energy at that point. So we could do K, instead of writing 1/2 mv squared, we could just write in that equation 0 equals Ke final minus Ke initial. Ke initial is 0, right? And we're after Ke final, plus, or sorry, minus mg times minus r over 3. And solve for Ke final. Finally, calculate the potential energy at point C. I think from memory of having assigned this problem before, the meaning is the potential energy here relative to what its potential energy is at the ground. So that's just going to be mg times 2r over 3. That's the height it is above the ground. That would give its relative potential energy. And that is it. Good luck on this homework.